Okay, 6.4 is on sine and cosine functions. So we're going to look at some of the graphs today. We're going to sketch some basic graphs. We'll look at amplitude and period. We'll also do some translations and model some real world situations. So here's an example of a sine function right here. Now you can get all this information from the unit circle because you know that at 0 the sine is the y value, which is 0. At 90 degrees the sine reaches its highest value up here, which is pi over 2, reaches 1. At pi, it goes back to 0. At 3 pi over 2, it goes to its lowest point, which is negative 1, and it just repeats. Okay. Now cosine is the same thing, only it starts off at its highest point and then repeats. So what you see is the same thing, just shifted back 90 degrees. So you see something like that. These are periodic functions where they go on forever. You can stick in whatever angle you want, so you can keep going around the circle. Therefore, as you keep going on with your angles, this is just going to keep repeating and repeating. The period is one full cycle, so it goes from here to here, would be the period. And the period is on the formula sheet, but that is 2 pi over b always. So for this regular sine where b is 1, this period is just 2 pi. Here's a better graph of the cosine that I just shared with you. It starts off at its highest value in the unit circle at 1, and then goes to 0 at 90 degrees, and then it goes to negative 1 at pi, and so on. Okay, the next problem wants us to sketch a graph of this, so I'm going to draw it out. It wants it from negative pi to 4 pi, so I wrote that out. And we're going to go up to 2 here. Okay, now I'm just going to start graphing points. So look at your unit circle, and the sine of 0 is 0. At 180 degrees, the sine goes all the way down. I'm sorry, it's back to 0. So every increment of pi here, we're back to 0. So I'm going to put zeros at all these places. And then in between here, it reaches its highest or lowest point. So at pi over 2, 90 degrees, it reaches its highest point, which in this case is 2 because the amplitude's 2. It goes down to its lowest point at negative 2, highest point in between here, lowest point. It just repeats this pattern. And so what you're going to find is it looks something like this. Okay, we're going to put these in standard form like this. I usually write D behind here. But basically, obviously what A is going to do would be the vertical stretch, which is going to be the amplitude. B is going to affect the period, as we'll find out. C is going to affect the phase shift, and D is going to affect the vertical shift. Just to give you an idea of what amplitude is half the distance between the maximum and minimum values. So for sine, for example, the amplitude is this distance right here, A. Okay, the period now is 2 pi over b. That's going to be really important. I put that on the formula sheet. Depending on what b is, this is going to affect the horizontal shrink or stretch, and it's going to affect then the period. So if you want to know what the period is, always take 2 pi and divide by the letter or number b here in front of the variable x. So here's an example then. We're going to sketch the sine of x over 2. So let's first find the period. The period is 2 pi over b, which in this case b is 1/2. So it's 2 pi divided by 1/2, which 1/2 goes into 2 4 times, so it's really 4 pi. So the period of the regular sine we know is 2 pi, but now it's 4 pi. So I'm going to put 4 pi here, and I'll make this about half that amount, so negative 2 pi. I'll just go from negative 2 pi to 4 pi here. So now I'm just going to start graphing points again. When you plug in 0, you still get 0, so the sine of 0 is 0. I'll do now pi, 2 pi, 3 pi, and 4 pi. So at pi, it ends up being pi over 2. So on your unit circle, the sine of that value is 0. And then at 2 pi, that's going to be 2 pi divided by 2, which gives you pi. The sine of pi is, once again, 0. And I'm sorry, I got to go back and do pi again. Pi over 2, the sine of is the y value, which is 1. So it reaches its highest value at 1 at that point. So I had this point wrong. And then at 3 pi over 2, the sine is negative 1, so it's going to reach its lowest value. And then 4 pi, you can follow the same pattern. 4 pi divided by 2 is 2 pi, and the sine of 2 pi is back to 0. So what this thing looks like if you follow this pattern, it looks like this. And so now the period repeats every 4 pi instead of every 2 pi. So what we, in a sense, did was we did a horizontal stretch of a factor of 2 from our regular sine function. So here's a summary then of all the important information: the amplitude, the period, sine and cosine written in standard form, and also the left and right endpoints can be found by solving these equations right here. That can be helpful too. It might be something you want to use. So let's try another one then. Let's sketch a graph of this. This is -3 cosine. Now I'm going to pull out a 2 pi here, and I'm going to have left over x plus 2. And I'm going to do that because b I know is 2 pi. So I can find the period. The period is 2 pi over b. So it's 2 pi over 2 pi, which is 1. So this thing is going to repeat every one time. And then also this thing is shifted over now, and I can find out how much it's shifted over. It's shifted over by 2 to the left. And then the amplitude is 3, but it's going to be also reflected. So this is going to be a little bit harder one to graph. So let's start graphing some key points in the unit circle again. Let's first start with 0, right here. If you plug in 0, we get 2. 2 times 2 pi is 4 pi. The cosine of 4 pi is back over here, and so that value is just 1. So that's -3. So all the way down here first. Now, this thing's going to repeat one full time within a cycle of 1 because the period's 1. So I'm going to do, so we can go ahead and plug these points in then, because we know the period is 1, so it's going to be repeating itself. Now, obviously then, I can figure out that this thing is going to be reaching its highest point at 3, right here. And then it's going to hit the 0 in between both those places. And you can try to plug those in if you want. Like plug in a half, for example, for x. If you plug in a half for x, it's going to be 2.5, 2.5, and then times 2 gives you 5. So that would end up giving you 5 pi right here if you plugged in 1/2. And the cosine of 5 pi is over here. And that's -1. So it's going to end up being -1 times -3, which gives +3. So it does give its highest value. So you can follow that same pattern then, break this into 4 equal parts, and know that it hits zeros here and it reaches highest value right in between. Same thing here. And that's the best way to sketch this function, which looks like this then. And you get the idea. But this one has been shifted. It's been reflected over the line y equals x because cosine normally, would go like this if it wasn't negative. And basically we can graph it pretty easily by just picking points, making a table from the unit circle. What's nice about these sine functions is they can be used in real life situations for electric currents, because currents, as we know, are alternating electric currents with a certain frequency. Musical tones are just sound waves that there's high pressure air and then low pressure air and then high pressure air, and so basically you end up representing that with like a sine, where the high pressure would be the peak and the low pressure would be what's called a rarefaction. Radio waves, obviously the same thing, only now with electromagnetic radiation. Tides, the high tide would be the high, low tide would be the low of the sine wave, and also weather patterns. Okay, so here's the last example then. Let's say that we have the depth of water y at the end of the dock in Bar Harbor, Maine, and it varies with the tides. The table shows the depths in feet at various times during the morning. So we have the time and we have the depth. Okay, what we're going to do is answer some questions about this. So let's answer, let's find a trig function to model the data. Let's find the depths then at 9 and 3, and answer part C as well, which is that a boat needs at least 10 feet of water to moor, or what times in the afternoon can it safely dock. Okay, now the easiest way to get this, to be honest with you, is in your calculator. If you go to Stat and you go to Edit and you enter these values in for L1 and L2, then when you go to Stat Calculate now, you can scroll way down to Sine Regression, which is C here. So I believe I can just hit, I'm sorry, I'm going to scroll up to it and hit Enter. And then it asks for iteration, so it asks for how many periods do you want basically, and the period it's asking for, which I'm going to put in 12 because the tide should change every 12 hours. It should be the period based on because we know the tides come from the moon. We're going to store this regression equation in var's y variable function y1, and we're going to hit calculate. Now we can take a look at this graph. Now, one thing you might want to do, I've also got my stat plot turned on, and you might want to turn that on, and you might also want to go to zoom stat, so that way it automatically fits the window. So what you're going to see now is it fits the data that we entered in because we have our stat plot turned on here, and then the function that it calculated goes in for y1 so that you can see this. And now we can answer the questions that they wanted us to answer, because we can write the function right here. We can find the depths at 9 a.m. and 3 p.m. Pretty easily in this table. Just plug in 9 for x, so go to stat calculate value, plug in 9, and it'll give us the depth there, which looks like about 1.49 feet. And we could do the same thing for 3. 3 p.m. is actually 9 hours after midnight, so we would plug in 9 for that. When we go to second calculate value, we'd plug in 9, and that would give us the depth at 9. And I'm sorry, then I'd have to redo the other one. The other one was at 9 a.m. 9 a.m. I'm sorry, 3 p.m. would be 15 afterwards. So I'd actually have to do second calculate value 15. 3 p.m. is 15 hours after midnight. And that gives me the depth, which looks like it's about 8.6, 8.7 feet. A little hard to see that. And the best way to answer the question of the boat for part C needing at least 10 feet, we can graph 10 and for y, and just look at when the boat needs at least 10 feet. We're looking at between these values here, which look like we're talking about 1 to 3 a.m. to about 4, 5, 6 a.m. So from about 3 to 6. And then also over here, if we add 12 over here at 15 then, which is about 3 p.m. to 6 p.m. That's probably the easiest way. Now you can write this equation by hand too without the calculator, and it is tricky, but it can be done because we learned our equation was y equals a sine of bx plus c plus d. So we can figure out how much it's been shifted up by taking the highest value 11.3, subtracting the lowest value 0.1, and dividing by 2, which gives us 5.6. And that's also the amplitude. And then the period, we know we can plug in 12 for that. Actually, I'm sorry, the period is equal to 2 pi over b, which is equal to 12. So actually I would do 2 pi over 12, which is pi over 6. So I'd enter in pi over 6 for the period. And then you can figure out the phase shift by grabbing 2 points from the graph. So I actually typed this in already, so I'll just turn this on for you. And you'll see that it's pretty close. I think I phase shifted a little bit to the right, and my period's off a little bit, but you can adjust those things. In fact, one way is to look at the y-intercept here. So at 0, you're at 3.4. So one way to ensure that you have the right c now is plug in 0 for x and plug in 3.4 for y and solve this equation. Right here, I would subtract 5.6, divide by 5.6, and take the inverse sine, which gives me, all right, so you see that it matches 0.4 was what c ends up being, negative 0.4, if you solve this. So that's a good phase shift. But you can tell my period's a little bit off still, so maybe I want to change my period to 13, in which case this would be period equals 13 hours instead of 12. In which case we'd put 2 pi over b, and it'd be 2 pi over 13 for b. So if I plug that in, so now you can tell now that I adjusted my b to be, once you multiply both sides, 2 over 13 pi, and plug that in for b right here, 2 pi over 13. Now you can tell that it matches it very close. So now we've got a function that models the actual tide. So we can then predict any depth based on the time of day, which is really handy.